get started with our second talk on deep learning for intercarbon field monitoring. Our first speaker is Petar Djuric, who will be speaking to us about Gaussian processes being applied to assessment of the fetus during labor and delivery. So I'll hand it over to Mark.
Thank you, Ted. Hi again. So I think I don't know how the next talks will be, but this will be a talk with equations. So I apologize ahead of time. I will try to explain the equations though in a way that is friendly for those of you who are not used to equations. So it is a presentation on using deep Gaussian processes for monitoring, and this is work done together with my colleagues from the medical school, Djuric and Sandra Hazelman over there, and also two students, Yuha Liu and Marcy Ajra, who do not come here because of these issues. It's complicated. So this is the outline. I will first briefly introduce you to Gaussian processes and deep Gaussian processes, and then to two models that we use to monitor Petar tracings, Gaussian process state space models and deep Gaussian process state space models. And then I will show some experiments with field calculated tracings. So this is an ongoing work, so you will not see final results. You will see where we are stuck at this point. And but you also see that why we are excited about where we are going at this moment. So first, a Gaussian process is a stochastic process that is used in probability theory. What is important about this process is you take any number of samples from the process. This vector of samples will have a Gaussian distribution. That's all one needs to know about this. And it's very easy to work with. It has two major parameters. One is the mean, which is denoted here by M, and the other one is covariance with K. So this covariance K has some parameters theta. So Gaussian processes are becoming more and more important machine learning tool, and they have an interesting way how to explore similarities in machine learning. Machine learning is all about to find similarities. If A is similar to B, using A from training data, you can predict what happens with B. That's all it's about. Not only Gaussian processes, any machine learning. So M is the mean function, K is the kernel of covariance function, and theta are some hyperparameters that one learns during training. So we have training data and we learn these parameters. So here is one slide with examples from two types of Gaussian processes. On the top is two realizations of a Gaussian process that use one type of covariance function that actually simulates smooth data. Whereas the bottom one is one with much more rigid data. So the choice of this kernel function is important in doing machine learning with Gaussian processes. So what is so beautiful about Gaussian processes compared to other machine learning methods? Number one, they're not data hungry. We don't need millions and millions of data to do machine learning with Gaussian processes. Second, one can easily employ the Bayesian paradigm to do machine learning with Gaussian processes. What that means is all the results are provided in probabilistic terms. So, what you see here is equation 1 is a vector y which represents observations. So this can be a vector of field heart rate tracings. What you see here as f of x, this is some function. So these tracings are a function of some input vector x. X is input vector. So the job of the Gaussian process is to find this estimate f. So we are actually in the business of estimating functions, unlike parameters. That's much more complicated. And epsilon here is noise. So here is the beauty. So we have a function f that is treated as a random object. And you have a distribution of this function, and this distribution is Gaussian. And then you observe data y and input matrix x, and you construct what is known in the Bayesian theory as the posterior of the function. So what you have learned about the function from this model and the input-output data. So this part here is the prior, which is the Gaussian prior, right here, and this is the likelihood, which is easy to obtain from this function. So here is an example. So suppose you have a function that looks like this. So this is a time function, and it represents the ground truth. And then you have noisy version of it. And then you would like to estimate this function using Gaussian processes. So what you do first is you can generate some samples from the prior. This is how it looks. It doesn't resemble at all what the true function is. But once you apply the data, the observations, this is what you get. It's fairly close to what you started, what the ground truth is. So we estimated the function, and these are some samples from the posterior. So one more slide that shows what Gaussian processes are. So you imagine that we have these observations that are with plus symbols here, and then what you estimated is this particular red line. This is the mean, and this shaded area represents your uncertainty about the function, how sure you are that this is your function. And you can see here in this part, it's you're much more sure than you are maybe in this part near the ends, because there are no data that go beyond this time. So again, I repeat, what is beautiful about Gaussian processes, all the results are probabilistic, unlike in most of the deep learning methods. That's one of the main problem. They only provide one number, and you have no idea how accurate that number is. So this is now what deep Gaussian process is. So suppose you have input z here, that was x in the previous slide, and what you now do is you create this chain of latent variables, and these are not known. So you go from z to y, and so y are the observations, x are latent variables, and z represent input variables. Every arrow here is a Gaussian process. So there's a function here that takes you from z to xh minus 1, another function that takes you from xh minus 1 to xh minus 2, and so on, until you reach the observations. The reason why you want to do this is because with deep Gaussian processes, you improve the capacity of learning. So you can actually model a very nonlinear function with deep Gaussian processes. So again, we will take this z and this y, and we will try to learn these latent variables. And of course, in machine learning, we do two things usually. One is to classify, and the other one to predict. So we move on now to Gaussian state space models. So this is an example of a Gaussian model, Gaussian state space model. So we have observations y1 to yt. These x's here represent hidden states, and the y's are the observations. So a Gaussian state-based model would be one where these links here and these links, the arrows, are functions that we don't know and that we want to estimate. So this is the key. So unlike standard state-based models where you know the functions, here we do not know the functions. And just given the observations y1 to yt, we want to estimate all these latent variables and also the functions that connect these variables. That's a big ask. And this is the mathematical model how we do it. So in brief, we use something that we call random vectors, random feature vectors, px, that are represented by this vector here. Remember, the x's are now these hidden states, And rho are vectors that are sampled from a par spectral density of what is the kernel of the Gaussian process. That's the covariance function that we want to use for the Gaussian process. So what is known to us are the rows, because we sample them randomly. And then what is also known to us, so here we don't know it, but what we will do is we will assume for now that it is known. And then we want to estimate these theta parameters, and then these psi parameters. So the overall objective here is, in this model, this complicated model, to estimate theta, and to estimate x, and to estimate psi. And this can be done in a very nice way using also common filtering. And this model still is very nonlinear. Why is it nonlinear? Look how these x's enter your model. There's no linearity here. And this is how a deep Gaussian state space model looks like, Gaussian process state space model. So you have the observations here, the bottom row, and these are intermediate layers of processes. And then this is the bottom process, what we call also the root process, and this process is of interest to us. So our objective is to estimate all these processes, and in particular we are interested in this most basic process. Here's what's happening. Y is a vector, could be a high-dimensional vector of observations, of features, and then we try to estimate these latent processes. And when we are going from deeper and deeper, we reduce the dimension of the process. This is something that Rick was talking in the first talk when he was doing compression. So in doing this, we want to actually find this process, xlt minus 1, and then use this process to either predict or to classify. So these are the equations. I will not go over them. Instead, I will only say that we have a methodology to estimate all the unknowns of the process. And here I would like to show how it works on synthesized data where we know the truth. So here we have only two-layer deep Gaussian process with three processes in one of the layers, the first layer, and two processes in the second layer. One of the curves represents the ground truth, so we generated the process according to the model. And the other curve represents the estimate of that hidden process. So one of them is the truth. In this case, it is the red curve, and the blue curve represents the estimate of the process. While we are doing the processing, we had no idea what the functions were. All these functions here, we had no idea what they were. So we didn't know the parameters, and we didn't know the latent processes. So only what is plotted here are the hidden processes. So with this progress we made. Now we wanted to go now to field hardware tracings. So here's what we did. We took two groups of field hardware tracings. These are Stony Brook data now. One group were tracings from healthy born babies without any issues, and the other group were from tracings of babies that ended up in NICU with HIV issues. So what we wanted to see is if this compression that we were doing by doing Gaussian by using Gaussian process state-based models, if we could find differences in the patterns of the data. So the top three plots are plots of good babies and the bottom of bad babies. One axis represent, so in this particular example, we use a single layer, so it was not a deep process, and the dimension of the hidden process was 2. So the way how we did the processing was the following. We took 10 seconds of data. This is 40 samples for 4 samples, we used median filtering, took the median value of the 4 samples, and that was the representative of the second. So this is how from 10 seconds of data, we went from 40 samples to 10 samples. So then we projected these 10 samples on a 2-dimensional space. And these segments of 10 seconds were overlapped 50%. Something similar is done in speech processing, for example. So it may not be immediately apparent here that there are differences, but we notice that for the babies that ended up in NICU, they have moments of time when they actually spend some time away from the cluster that they tend to occupy for some time. More interesting results were obtained with 2-layer processes. So here we have, again, on the top, good tracings, projections of good tracings, and the bottom projections of bad tracings. So this again goes with Austin's remark earlier today, I think, when he said, why do you use what we use in our practice? Why don't you use just machine learning? Don't be biased with our way of thinking. So this is a way maybe to go away from you and then try to see what the machine learning methods would see on their own without any assistance. You still have to come back to you to find out if this makes sense, of course. So again, you can see here that there is less regularity in these top patterns and more regularity in the bottom pattern. This reminds me, actually, I don't know if any of you have done analysis of brain signals. People in coma have these periodic patterns that one observes if one, again, projects the data from, say, LFP data to low-dimensional spaces. So these are manifolds with very low dimension. So this, again, are data obtained by using 2 layers. So what we do is we go from dimension 10. So these are the raw data, dimension 10. Then we project them to lower dimension space, 3-dimensional, and then one more time to 1-dimensional space. So these 1-dimensional spaces, of course, are easier now to follow for at least for visual purposes. So, and this is an example where okay, one more example with 10.3.1. Again, you can see the periodicity in the, apparently one can claim that one see differences between the 2 sets of projections. And the next 2 slides show results of real data with 2 layers, but now we go from 10 to 5 and 1. And again, apparent periodicity here and not so much in the top set of plots. One more set of examples. So now our challenge is several-fold. So we just at least got encouraged that we see differences in the projected data. Our aim is the following. We would like to, in fact, borrow ideas from speech processing, where in speech processing, when they do speech recognition, they actually go after the phonemes of words. And then based on the estimated phonemes, they can recognize the word and so on. So here we want to find an alphabet from these examples, or if you like, phonemes. And then based on these phonemes, to recognize the moment when, because we're doing monitoring in real time, when the fetus needs attention. So what that would mean is we will again project even these data to a sequence of alphabet or letters, and then based on these letters, we would like to raise the attention of the attending clinician that the fetus may be interested. So of course, the idea is not to stop there. In a later stage, we would like to also explain why the method actually chose to alert the clinician that the fetus is at risk. So there has to be this explainable component to the experts' why exactly the machine is choosing to alert. So, in conclusions, we are working with Gaussian state-based models, deep and non-deep. What is very important is that we are working with time-varying models. What that means is, in the beginning, maybe everything was fine, and then it got worse. These parameters that you saw, let me just go back quickly. Here. These parameters are time-varying. See this peak? They change with time. And this method has a very good way of how quickly it forgets what was good at some point and is not good anymore. So they're time varying, and this would allow us to capture the possibilities of changes in the well-being of the fetuses. So our initial results suggest that the projections of the segments of raw FHR tracings on these lower dimensional spaces are indicative of something that is of interest. And future work includes now identifying the good and bad time segments of the fetuses and using these, not only that, but also using UA signals and clinical data to further improve the prediction of the method. So I'll stop here and I'll take your questions. Thank you.
Thank you, Petar. Do we have any questions from the audience? Martin?
It's a great talk. It might be the first time I'm beginning to get a sense of the Gaussian processes in this way.
I would like to ask for the step where you did the projection to lower dimensional space. Do you think there is a data loss happening there? And sort of the adjacent question right after, what if we applied conventional nonlinear complexity estimates straight to the 10-dimensional space, and sort of, yes, it would be not easy to visualize, but it would potentially be able to capture the entire basically richness of the data.
Yes, first answer to the first question, every compression, every projection includes loss of information. Absolutely. Obviously, our intention here was to reduce the observation space to a low dimension space, and then with again using, we're still not there yet, to use the projected trajectories to disentangle the good from the bad. So, and this is again work in progress. So obviously there are alternative approaches. Again, the reason why we chose this method is, number one, it is very coherent. It is based on the Bayesian theory. Second, it provides probabilistic results. We can claim, again, in probabilistic terms, how sure we are with our either classification or prediction. I have results also on prediction. You will be surprised how well it actually predicts.
And a follow-up to Martin's question is, do you think there's a relationship between these results in lower dimensional space being skewed with complexity analysis and entropy, where we often see that pathological cases have reduced entropy?
So I will comment on this by using the example from brain signals, because we have tried it on brain signals, because we have access to signals, people who are in coma. And we use actually complexity analysis of these projected data on low dimensional spaces, and we do find big difference between people in coma and people who are not. So I would expect that, again here, that the signals of the projections of fetuses who ended up in EQ are simpler than those of coronal. So this could be one maybe metric also, how to measure how far they are from, say, normality, or how far the normal is out from being actually not normal. So there may be some good ways of inventing new metrics to measure the well-being of kids. And of course later we have to figure out what does it actually mean for people who will be using eventually these kind of metrics.
Other questions?
There's one over there.
So you said you are estimating the latent process and these 5 side functions. Do you assume your perturbation noise to be known, and or is it just a hyperparameter that you then do some additional search over? And if it is known, then especially with multiple layers, how do you know it's going to change?
Right. So the question is, what is assumed about the noise? The only thing about the noise that we assume is that it is of Gaussian nature. And the reason why we assume it is Gaussian because the Gaussian assumption is the maximum entropic assumption. Every other assumption will be more informed. But other than that, we don't assume anything. And it turns out that the Gaussian assumption will lead to some interesting analytical solutions to some point. I did not hear.
I think we need the microphone.
Yeah, so we use
Just come closer.
But also the hyperparameters over the Gaussian, so like the standard deviation of it. Do you do any search over that, or
if I do what?
a search over the standard deviation of your noise?
So the hyperparameters are also random. They have their own priors, and they are treated in the same way as the hidden state processes. They're all unknowns. They're treated in the same way. And the nice thing about, we go back to the equations. So we have, as you can see, the unknown parameters psi and theta, they are actually linear conditioned on x. If you know x, they're linear. There you apply the common filter. Now, once you estimate the psi and the theta parameters, then you have to estimate the latent processes, and they're nonlinear. I didn't mention this, but to estimate the latent processes, we use particle filtering. So it's a two-stage. It's just estimate the hidden process, estimate the parameters. Estimate the hidden process, estimate the parameters. And as I said, what is embedded in the model, we allow for these parameters to change with time.
Do you foresee some promising ways to relate these, to use the speech analogy, to find phonemes that you can talk to the clinician about? Would the complexity of one of the low-dimensional spaces be one such?
Yeah. So one direction of work is to find how many letters there are. So this is again related. Everything has to be unsupervised. So how many letters in the alphabet we have, and what they actually mean, and then what the sequence of letters actually represent in terms of the well-being of the kids. I can imagine maybe easily that we have 4 letters that are very bad if they're next to each other. If they same letters appear sporadically, that's not a big deal. So these kinds of things we want to discuss.
Do we have maybe room for one more question before we go on to the next speaker? Okay, thank you so much, Petar.
Thank you.